and welcome to another video. We will be taking another look at electrostatics and charge. This is part 2, where we're going to be looking at Coulomb's law and electric fields. First, let's take a look at Coulomb's law. The mathematical formula for the electrostatic force is called Coulomb's law, after the French physicist Charles Coulomb, who performed experiments and first proposed a formula to calculate it. The equation that you can see here, F, which is force, which is measured in newtons, Q is a charge, the SI units is coulombs, R is the distance between charges with an SI unit of meters, and K is a constant derived from the permeability of free space. K is approximately 9 times 10 to the 9 Newton meter squared per Coulomb squared. Be sure to use SI units before attempting to use the formula. This is because, as you can see, the constant is made up of the SI units, newtons, meters, and coulombs. Because it's a vector force, it can be expressed in terms of x and y directions. Coulomb's law only gives the magnitude of the force. The position of the charges will determine the direction. The electrostatic force is a vector quantity and is expressed in units of newtons. The force is understood to be along the line joining the two charges. Let's take a look at forces between like and unlike charges. The magnitude of the electrostatic force between point charges Q1 and Q2, separated by a distance r, is given by Coulomb's law. Note that the Newton's third law, every force exerted creates an equal and opposite force, applies as usual. The force on Q1 is equal in magnitude and opposite in direction to the force it exerts on Q2. As seen in A, the like charges repel, and in B, the unlike charges attract each other. Let's take a look at the similarities of electrostatic force and gravitational force. As you can see, both look pretty similar. They're both measured in newtons, that is the force. They both have a universal constant. Electrostatic force has a constant K, while gravitational force has a constant G. They're both proportional to a product. For electrostatic force, it's the product of two charges. For gravitational force, it's the product of two masses. They are both inversely proportional to the square of the distance between two objects. On an atomic level, gravitational force between protons and electrons are negligible in comparison to electrostatic force. The reverse is true on a planetary level. Let's look at the concept of a field. A field is a way of conceptualizing and mapping the force that surrounds any object and acts on another object at a distance without apparent physical connection. For example, the gravitational field surrounding the Earth and all other masses represents the gravitational force that would be experienced if another mass were placed at a given point within the field. In the same way, the Coulomb force field surrounding any charge extends throughout space. The Coulomb force due to a positive charge, Q, is shown acting on two different charges. Both charges are the same distance from Q. Since Q1 is positive, the force, F1, acting on it is repulsive. The charge Q2 is negative and greater in magnitude than Q1, so the force F2 acting on it is attractive and stronger. The Coulomb force field is thus not unique at any point in space, because it depends on the position and the value of test charges Q1 and Q2, as well as the charge Q. Calculating electric field of a point charge. Here we have two equations that we can use to calculate electric field. One is force over charge, and the other one is that constant K, the 9 times 10 to the 9, times the charge divided by r squared. So F is the electrostatic force, SI units in newtons. Common Q is the charge of an object in the field, produced by the source charge. SI units, coulombs. K is the constant. Big Q is the source charge. So you'll notice that we used a lowercase q as the test charge, or the charge being affected, and uppercase Q for the source charge. R is the distance from the source charge to a point in the electric field.